several attributes for the cubic equation of state, whereby it represents differently. So basically, they have A and B, but please be careful for Redlink, Kwong, and Peng Robinson, because their definition for A and B is quite different. So don't and should not be interchanged. All right. So for Rashleigh Kwong, so you can refer to these ones, A and B is presented by this equation, by this term. And for Peng Robinson also, this is respectively, it is almost equal, right? So but so don't be confused, just the value is different. Okay. Okay, I have one question for you. uh, because there are several, you can give your opinion in the section, in the comment section below. There are several and various could be equation of state, right? So can you identify, or maybe you can give an opinion, what are the difference between one equation and another one equation? Is it similar, and if so, why? And if it's not similar, then if so, why? Okay. All right. Okay, using the van der Waals equation used. Oh no, I don't think I have to skip that one. Okay, thank you. Okay, next one is virial equation of state, whereby the power series expansion in P is expressed as PV equals to A plus BT plus CP squared plus dP cubic, plus if B we can represent it by AB and C by AC and D by AD, then you can summarize it, or you can rephrase it as PV equals to uh, in bracket 1 plus BP plus CP plus CP squared plus DP cube, and so on. Okay, for the virial equation, actually, virial equation of state is derived from the first principle using the statistical mechanics, and the equation is given by a power series expansion for the compressibility factor, which is Z, expressed either as a function of density, which is a reciprocal of V, PV per RT equals to 1 plus P per V plus C per V squared plus D per V cube plus so on, or pressure. It can be either in the terms of volume, or reciprocal of volume, or pressure. Okay, so it's for the pressure, this is accordingly. And whereby we can see that for the ideal gas, temperature and R constant, as the P is approaching zero, the limiting value of PV here will be, sorry, this PV, yeah, this PV, actually it's the same. If let's say the consistent, right, as the P approaching zero, the limiting value of PV will be the same for all four gases. In this limit, we can see it becomes PV equals to A, or to the function of Ft. So this is the function of Ft, because the limiting values are used to establish a T scale which is independent of gas used as thermometric fluid. So this is one statement that you can take note. So whereby if let's say we rearrange again, making it PV equals to A equals to RT as the ideal gas, and assigning the value of 273.16 to temperature of triple point of H2O, right? So it can be PV equals to R times 273. Yeah, that's a triple point for water. 647. Oh, this is, and dividing the 7 and 8, so we can get T equals to 273.16 the bracket PV per PV, because we can see that RT can be represented by this one T, so it is divided 7 and 8, so we can get this one and this one, this one and this one, because this will give indication that is known as ideal gas temperature scale, whereby when P approaches zero, the gas molecules become more widely separated by infinite distance, and the volume of the molecules decrease and become negligible, and the intermolecular forces between the molecules is approaching zero. At this condition, the gases are said to be ideal. Right? So this one applies to the ideal gas. And then for the B, C, and D, etc., are the virial coefficients, whereby B equals to B per RT and C equals to C minus B squared per RT squared. And so, in this conclusion, which power series to use, uh, which is truly depends on which parameter is needed. So it might be different, it might be a different equation and different equation state and different terms, so it should be totally depend on which parameter is needed in the question or in the situation. And for relatively low pressure, which is up to 15 bar, using the pressure expansion series up to the second virial coefficient is sufficient. And for the higher pressure, pressure up to 50 bar, using the density expansion factor up to third video coefficient is more accurate. So these are the tips for the period equation, especially for the second term and the third term. Okay, we move on to the general. Sorry, this one is not covered. Okay. Okay. There's one thing, or maybe one. Uh, maybe you can call it tips. If let's say the water, or in the form of steam, you can refer to the property table straight away. And for ideal gas, for example, air, nitrogen, helium, etc., and you can use PV equals to MRT or other relation suitable, and H plus CPT, specific volume. Sorry, and and U, this is the CV times T. Okay, and etc. So basically, these are the main guidelines for water and ideal gas. And another one point is the, if let's say the situation mentioned about it is a rigid tank, then it should be the constant volume, which is V is constant, and for the frictionless cylinder or freely moving piston, it should be the constant pressure, whereby the pressure is constant. Okay, so I think that's all for today, and so I hope that you are really understand, especially in how to derive and everything. And basically, you just have to understand the equations. You don't have to really memorize it, right? Right, of course, because usually it will be given, or you can bring the equations. So I think that's all for this chapter. So for the a reflection or maybe the insight, maybe what someone or maybe all of you can give a recap on what have you covered in chapter 1, volumetric properties. of pure substance. Okay, all right, thank you. So see you for the next chapter, next in the next YouTube link. All right, thank you.